Okay, so we are going to perform Lab 3 series RLC circuit. This experiment consists of 3 circuit setups, one RC circuit, one RL circuit, and one RLC circuit. To perform this experiment, we would need these components: 100 ohm resistor, one 1 microfarad capacitor, a 330 microhenry inductor, a breadboard, a function generator, and a digital storage oscilloscope. So first we are going to construct this RC circuit and take the relevant readings. We are going to record the readings in this relevant section of the datasheet, table 1.1 and table 1.2, which is marked for RC circuit. First of all, we are going to measure the practical value of the components, the resistance, the inductor, and the capacitor. So using a DMM, we are going to measure the practical resistance of the resistor. So we are going to connect the resistance to the breadboard and then take the reading. To take the reading, we have to take a DMM, set it up for resistance measurement, and then connect the probes across the resistance. Here we can see that the practical value of the resistor is 97.5 Henry. 97.5 ohms. We are going to record that value in this table over here. Since we are going to be using the same resistance for all the experiments, we are going to record the same value for RL and RLC circuit as well. So 97.5. So we have recorded the practical value of the resistance. Now we are going to measure the practical value of this capacitor. We are going to do that using a LCR meter. We can also measure the practical value of the capacitor using DMM, but we are going to use the LCR meter since we have this available. So one important distinction is this capacitor. This is a electrolytic capacitor. This electrolytic capacitor, if you notice, have two legs, one long leg and one short leg. So this capacitor has polarity. The longer leg is plus and the shorter leg is minus. So when attaching the capacitor to the LCR meter, we are going to have to use this polarity. You can see that the plus and the minus polarity is marked, so we are going to attach the capacitor accordingly. Since we are going to measure in the range of microfarads, we have to rotate the knob to that position. There is an offset value of 0.004. We are going to try to eliminate it by using this calibrator. So okay, so our LCR meter has been calibrated. Now we will attach the capacitor to this unit here. We can see that the practical value of our capacitor is 0.942 microfarad. So 0.942 microfarad is the value of our capacitor, which we are going to record in this table. We we're also going to record the same value in this RLC circuit table. Okay, so now we're going to construct the circuit. We are going to construct the RC circuit, which is a simple series circuit. So this resistor is already attached to the board. We'll connect the capacitor in series to this resistor. So we're going to attach this long leg of the capacitor to the node connected with the resistor, and attach the other leg in a separate node. So our circuit has been connected in series. The capacitor or resistance have been connected in series. Now we're going to attach the source with this circuit. This is the probe of the function generator, and we are going to attach wires to it before we can attach it to our circuit. So we are opening the crocodile clip and attaching the wire to the crocodile clip. So okay, so wires had been attached to our crocodile clips. Now we can connect this to our circuit. So according to the circuit diagram, the plus end or the red wire should go to the one end of the resistor. The minus wire, the minus polarity, the black wire, should go to the node connected with the capacitor. So we're going to do that now. I'm attaching the red wire to the end, to the node connected to the resistor. And I'm going to connect the black wire to the node connected with the capacitor. Okay, so our circuit construction has been completed. You can see that the source has been connected to the series R and C components. Now we have to calibrate our function generator to give 3 volt peak and 10 kilohertz frequency as output. So to do that, we have to turn on our function generator. I'm turning on the function generator by pressing the power button located here. So we are required to set the function generator to 3 volt peak and 10 kilohertz. So first we are going to adjust the frequency of the function generator. It's always a good practice to set the frequency first and then adjust the amplitude of the function generator, because with frequency there will be slight deviation of the amplitude. So we should always set the frequency first and then set the amplitude. By rotating this knob, I can change the frequency, but taking it to the max position, I see that the output frequency is 6.2 kilohertz. So to get the required 10 kilohertz, I will have to change the range, which is currently selected at 1K. So I should shift to 10K so that I can set the range of the function generator and generate 10 kilohertz. So let me rotate the knob to the left first and then press 10. Now you can see that the output is 5.1K. If I keep increasing by rotating the knob clockwise, you can see that I can reach 10 kilohertz. So our frequency has been set. Now we have to set the amplitude. By rotating this knob, we can set the amplitude. However, this display does not show the amplitude of the function generator. To set the amplitude, we will have to connect the function generator to the oscilloscope. So now we we are going to attach the oscilloscope to this circuit. So these are the probes of the oscilloscope. This is channel 1 and this is channel 2. We are going to use channel 1 and connect it to the source so that we can set the amplitude. Before connecting the probe, we have to attach wires to the probe so that we can use it. So this is a crocodile clip and we are going to attach it as before. This is the positive probe which we will use to connect to the node we are going to get the measurement of. To connect wire to this probe, we'll press down this portion of the probe which will expose the connector. We'll place our wire and release, which will lock the wire to the probe. Now we can attach this to our circuit. It's a reminder that the black wire should always go to the ground of the circuit, and we can attach this positive part, this probe, to any node we want to make measurement of. So I'm attaching this to the ground, which is located here, and I'm connecting this plus wire to the node connected to the source, which is here. So this oscilloscope's black wire has been connected to the ground. The black wire of the function generator and the black wire of the oscilloscope is in the same node, and the red wire of the function generator and the plus end of the probe is connected to this node. So we are now ready to get measurements from the oscilloscope. Now we'll attach channel 2 to our required nodes so that we can take the required readings. Each and every lab manual states descriptive procedure which outlines all the steps necessary to complete the experiment successfully. We have been following the procedure so far, and now we are going to connect channel 2 to node P, which is this node of the circuit. So this node of the circuit in the breadboard is the node where one end of the resistor and one end of the capacitor is connected. So if we look at our circuit, we see that this node here is where this resistance and capacitance has been connected. So we are going to attach the positive part, or the positive portion of the oscilloscope probe to this portion, and the black wire of the probe should always go to the ground. Before connecting the probe, we need to attach wires to the probe, and we are going to do that by connecting this wire to this crocodile clip and this wire to this portion of the probe. Now we're ready to connect this probe to our circuit. So we'll connect this black wire to the ground and positive part of the probe to node B of the circuit diagram, which is this node. You can see from the circuit diagram that the voltage at node B is the voltage of this capacitor, and the voltage of node A minus the voltage of node B is the voltage of this resistance. So if we look at our data table, you can see that the required readings are voltage of capacitor and the phase of the capacitor, voltage of the resistance and the phase of the resistance. I have calculated the theoretical value of these parameters and recorded them here, which you can do easily by solving the circuit. So now we're going to take the practical readings and record them in the table here. Okay, so we are going to turn on the oscilloscope. So pressing this button on top to power the oscilloscope. The oscilloscope takes a while to power up, and now we can see that a signal is being displayed on our screen, which is connected to the channel 1 port, which we connected to the circuit earlier. A very good practice that you should do is initially, if you see any unwanted, if you find any unwanted output in the screen, press the default setup button and then build the settings so that you get a clear output on your screen. So initially, this horizontal scaling, which is the time scaling, is too high for displaying this signal. So we are going to decrease the scaling. So now we can see a curve displayed in our oscilloscope. However, we can see that this is a triangular curve because, as we discussed earlier, the function generator always gives triangular wave as its default output. So to change this, we would have to change the output to sinusoid. You can see that the triangular source has been lit up, indicated by the LED here. If you press the sinusoidal button here, our output will be changed to sinusoid, which is reflected in this oscilloscope. You can see that the measure parameters is already being displayed automatically. If you don't see this menu, just press the measure button, which will display the required readings on the oscilloscope screen. So we have attached the source to channel 1 of this oscilloscope, and we have to set 3 volt peak as dictated in our circuit diagram. So we have to first set this reading or any block which we want to use to channel 1 voltage peak or channel 1 voltage max, P max. So I'm going to utilize this area for displaying the reading. So if I press this button, I'll get a menu which will show me all the different settings that I can access. So since we're going to set it to a voltage parameter, we have to select voltage, and then you can see that the source is channel 1. We don't need to change it because we have connected the source to the source to channel 1. The type is voltage peak to peak, VPP. We have to change it to Vmax. So if I press this button, we will get a list of options, and you can see that by pressing once, the Vmax has been highlighted. So Vmax has been chosen by default. After a while, the menu will disappear by itself. You don't have to do anything. Just press return to get to this measure window. So you can see that the amplitude is currently 1.76 volt. We have to increase it to 3 volt because the circuit diagram tells us the required source is 3 volt peak. So now you can see that channel 1 Vmax is 3.04 volt. So we have calibrated the source to our required circuit parameters, which is 3 volt peak and 10 kilohertz. So the frequency of 10 kilohertz is being displayed here by default. You can verify this by looking at this reading, or you can see that the display of the function generator is reading 10 kilohertz. So you can check the frequency by looking at either of these parameters. Now, by looking at the oscilloscope screen, we see that although we have connected channel 2 to the circuit, we don't see a second waveform in the screen. That is because channel 2 is turned off. So if I turn on channel 2 by pressing this channel 2 button, we can see that the channel 2 curve is being displayed. So also note that always, since we're using AC circuit, our coupling should be AC for both channels, because both our input and our output are in AC, so the coupling should be AC. So now we have access to channel 2. Now we can take readings that are required for this circuit. You can see from the circuit diagram that the voltage at node B is the voltage of this capacitor, and the voltage of node A minus the voltage of node B is the voltage of this resistance. So if we look at our data table, you can see that the required readings are voltage of capacitor and the phase of the capacitor, voltage of the resistance and the phase of the resistance. I have calculated the theoretical value of these parameters and recorded them here, which you can do easily by solving the circuit. So now I'm going to take the practical readings and record them in the table here. As we saw earlier, that the voltage of node P is the voltage of the capacitor. So if we take the peak voltage reading of channel 2, which is connected to node P, we will get the voltage of the capacitor. So this blue waveform, which is connected to node P, is the voltage waveform of the capacitor. So to take the voltage max reading of this this blue signal, which is connected to channel 2, we can edit any of these blocks to show that voltage. If I choose this block, I should press this button, and since we are going to measure a voltage, we should select voltage and then change the source to channel 2. The type is already voltage max, so we do not need to change it, and we can press return. So here we can see that channel 2 Vmax, which is the peak voltage of channel. Okay, we can see that the channel 2 Vmax is 580 millivolt, which is the voltage of the capacitor, which we are going to record in our table. To measure the phase, we have to calculate this delay. This delay is with respect to the input or source voltage. So as we know that this channel 1 is connected to the source voltage, so we can see the channel 1 curve in this yellow signal, and the blue curve is the capacitor signal voltage waveform. So we are going to measure the phase. You should notice that these two channels are in separate time voltage scaling, so we cannot compare their shape. If we reduce this to 1 volt, now we can compare these two channels by saying that channel 2 is showing a much smaller voltage than channel 1. You can only make the statement if these voltage divisions are equal. To measure the time delay between these two signals, we have to use cursor. You can access cursor by pressing this cursor button. We can press this. We can turn the mode to manual. So there are three options: manual, track, and auto. We will be using the manual mode. The type of reading that we are going to take is time, because we are going to measure time delay. So the type should be time, which you can access by pressing this button. Now the type is time. Source is channel A. Since we are measuring with respect to the source voltage, we should keep the source to channel A. Now you can see that we have two cursors, cursor A and cursor B. When cursor A is selected, represented by this white highlight, if we rotate this universal knob, one of the cursor will change its position. Okay. By selecting the other cursor B, by rotating this knob, we can manipulate that other cursor. You see that the other cursor is out of scope of the screen. You can bring it into focus by rotating to the left. You see the second cursor is now in focus. Okay, so now we are ready to take the reading. If you see that the axis line has been marked, this is an axis line which you can consider to be a 0 point. You can see that the peak of the source comes before peak of the capacitor. So you can say that the voltage of the capacitor is lagging with respect to the source. Since the phase is lagging, the symbol of the phase angle should be minus. So we should record that while taking the time delay reading. Now let's take the time difference reading. To do that, since cursor B is selected, I can move it to one of the peaks. So I'll move it to the peak of the blue signal, which is the capacitor. And I'll move the cursor A to the peak of the source signal. Okay. You can make much more accurate readings by changing the horizontal scales. So you can do that. So I'm going to do that. It gives me a much better visualization of the peaks, and I can get to a better reading zone. Okay, so we see that the time difference between cursor A and cursor B is represented by this delta T, which is 20 microseconds. We should record this in our table. So our delay is 20 microsecond, and as we saw earlier, the phase of this voltage is lagging, so we should put a minus symbol in the theta, which is the phase value practical. You can then calculate the value of the theta by the formula shown here, del T into F into 360. So our del T is 20 microsecond, F is 10 kilohertz, and into 360. You see that the value is 72 degrees. So we have measured the voltage and phase of the capacitor. Now we'll move on to the voltage and phase reading of the resistor. We do not need to change any wires to make the measurement for the resistor. We just have to we can turn the cursor mode off for now. We can do that by pressing this mode and turning it to off, and we can close this window. So if we look at our circuit diagram, as I discussed earlier, that the voltage of resistance of the resistance is voltage of A minus voltage of B, and we have connected channel 1 of the oscilloscope to this node A and channel 2 of the oscilloscope to node B. So by subtraction of voltage A minus and voltage B, get the voltage of the resistance. We are going to perform this subtraction in the oscilloscope. So we are going to perform channel 1 minus channel 2 so that we can get the voltage reading of the resistor. We can do that by pressing this math button. If we press this math button, we will get the math menu. You can see that the operation is plus. We have to change it to minus since we are going to perform a subtraction. So if you press this button, you will see that the operator will change to minus, and there are other options available, but we are going to enable this subtraction. So source A is channel 1 and source B is channel 2, which means A minus B, which is channel 1 minus channel 2. So we have performed the required operation, and you can see the output here. So this new blue signal is the voltage of the resistance. This waveform has been calculated by a math operation, which is a subtraction of the channel 1 and channel 2. So by taking reading of this blue signal, we can get the peak voltage of the resistor and the phase of the resistor. For signals connected in channel 1 and channel 2, we can use the measure button to get the values, but for signals which are generated by using the math function, we are going to have to use the cursor to make the required readings. So again, we are going to access the cursor by pressing the cursor button and turn the mode to manual, and this time we are going to take the type as voltage because we are going to take the voltage reading first. Now we have to choose the source. If you press the source button, you will see that you have three options highlighted: channel 1, channel 2 and math. So these are the three signals that are being displayed in the screen, and you can choose any of this to take the required readings. So what we are going to do is take the source as math. You can repeatedly press this button to take this, select this option, or you can use this rotator to change your option. So we are going to use math. You can see that the cursor's color will change according to the source you have selected. So since you have selected the math as the source, the cursor color is being replaced by the color of the signal. This is easy for us to distinguish what setting we are working on. So to take the peak voltage, we have to remember what a peak voltage is. Peak voltage is the amplitude, which is the difference between the axis, which is the voltage 0, and the peak of the signal. So we can take cursor B to 0 volt. You can see the appropriate reading by looking at the values here. So we will cursor B until we take it to 0 volt, which is the axis. Now you see that the cursor B reading is 0 volt and it is completely aligned with the axis of our oscilloscope. Now we will select cursor A and rotate this knob until we take it to the peak of the voltage signal, which is the blue signal. So by eyesight we see that the cursor is now at the peak. So del V, which is the difference between the cursor B and cursor A, will give us the appropriate voltage. So the voltage is 2.72 volt. We should record this in our data tape. From the oscilloscope, we found that the value of VR is 2.7 volts. So we have recorded that in our table. Now we will need to calculate the phase. So by changing the type to time, we can take the time delay, which we will use to calculate the phase. For taking the reading, we will look at the curves. If you compare it from the axis, you will see that the peak of the waveform of the voltage comes before the peak of the source, which means the voltage of resistance VR is leading. So the phase angle symbol will be plus. So we should record that in our table. So as previous, we will take cursor A to peak of this VR waveform, and cursor B to the peak of our source waveform. And as previous, we can zoom in a bit to make our readings more accurate. We can turn this menu off so that we can get a better. So let's take this to the peak of the source, which is right about here, and if we press this menu on button, you will get the menu back. We'll select cursor A and we'll rotate it to the peak of VR, which is here. So we see that the time delay is 2.6 microsecond, which we are going to record in our data table. A 2.6 microsecond, and the symbol is plus because it was a leading voltage. Now we are going to calculate the angle, which 2.6 microsecond, 10 kilohertz into 360, 9.36 degree. So we have calculated all the required readings for the RC circuit. We have completed taking readings for the RC circuit. Now we will move on to the RL circuit. You can see that the RC circuit and RL circuit are similar, only the capacitor is replaced by the inductor. Since we have the RC circuit constructed in our breadboard, we will just replace this capacitor with an inductor to build the RL circuit, RL series circuit very quickly. Before placing the inductor, we have to take the practical reading of the inductor, and we are again going to do that by using this LCR meter. The rating for the inductor is 330 microhenry. So we are going to move this knob to this 2 millihenry position, because this microhenry range is for up to 200 microhenry. So we are going to move the inductor to the 2 millihenry position. This is our inductor, and we are going to place it to the LCR meter and take the appropriate reading. Okay, we can see in the display that the value is 0.332 millihenry, which is actually 332 microhenry. So our practical value is 332 microhenry. We are going to record that in the table. Since we are going to use the same inductor in the RLC circuit, we are going to take this, write the same reading in here. Now I'm going to replace the capacitor from our circuit and replace it with the inductor that we just measured. So we have built our RL circuit by replacing the capacitor with this inductor. You can see that this end of the inductor is connected to this node with one end of the resistor, and this end of the inductor is connected to the ground. Our connection would remain the same for as for the previous RC circuit. Again, channel 1 is connected to the source, parallel to the source, which is node A. Okay, so just as in previous circuit, we have connected channel 1 to this node A and channel 2 to this node B. So we can take the peak voltage readings of the source and the inductor directly from the oscilloscope, and to get the voltage of the resistance we would have to subtract voltage A from voltage B, so VA minus VB. So we're going to follow the same procedure as in the previous experiment. Continuing from our previous setup, we'll turn the cursor off and we'll also turn off the match signal for now. So since we didn't reset the oscilloscope, channel 1 and channel 2 is coupled to AC. So from the measure window, we can see that channel 1 Vmax is now 3.2. We need to adjust it because continuing from our previous setup, we'll turn the cursor off and we'll also turn off the match signal for now. So since we didn't reset the oscilloscope, channel 1 and channel 2 is coupled to AC. So from the measure window, we can see that channel 1 Vmax is now 3.2. We need to adjust it because our source input is 3 volt peak and 10 kilohertz. So we have to adjust the source to 10 kilohertz and 3 volt peak. So channel 1 is our source voltage, so from 3.2 we have to reduce to 3, or as close to 3 we can get. Okay, so 3.04 volt is our input voltage. So our input has been set. So now from channel to Vmax we can take the voltage of the inductor. So the voltage of the inductor is 600 millivolt, which we should record in the table. So we found that Vp practical is 680 millivolt. Now we have to calculate the phase, and as previous we have to calculate the phase by using cursors. By pressing this cursor button, we have to turn to on. We have to press the cursor button and move the mode to manual, and the source should be channel 1 since we are taking the reading with respect to channel 1, or you can set it to channel 2 because the time scale is same, so you will get the same reading. Now we can zoom in a bit by moving the horizontal, and now we can put it. Okay, so before taking the reading in this position, notice that the inductor's voltage is appearing first, and then the source peak is appearing. So inductor is leading. So our phase should be plus. The symbol should be plus. So cursor B to the peak of the source and cursor A to the peak of the inductor, and we see that is 20.40 microsecond. We are going to record that in our table. So so we have recorded the time delay of the inductor, and by calculating we find that the angle is plus 72.0 degree. Now again, following the previous procedure, the voltage of R is voltage A minus voltage B. So we are going to perform this operation in the oscilloscope, because we have connected channel 1 to node A and channel 2 to node B. So we can use the oscilloscope to calculate channel 1 minus channel 2. By performing the math operation, the operation is selected as 1, and channel 1 is source A, channel 2 is source B. So this purple colored waveform is the waveform of the resistor. So if we take the required readings, we will get the required parameters. You can see that this source is moving around a bit. We can improve this by doing a couple of things, maybe zooming in channel 2, which was really flat, or moving in the source, or we can press our circuit connection so that we get some. Okay, so the readings seem to have stabilized. So now we can take the reading. So if you see, the peak of the resistance voltage is appearing after the peak of the source. So the resistor voltage is lagging, so the symbol should be minus. And now we need to calculate the time delay. We press measure, we press cursor. The mode is set to manual. The source should be math, and we move cursor A to the peak of channel 1. Let's zoom in a bit. Cursor A to the peak of channel 1, and cursor B to the peak of the math waveform, the waveform we got from the math function. You see that the time delay is 4 microseconds, and as I said earlier, the voltage is lagging, so the sign should be minus. We should record that in our table. So it's 4 microseconds. And the calculated angle is 14.4 degree. Here I have calculated the phase first, and now I will calculate the peak voltage reading. This is to show that it doesn't matter in which order you take the readings in. As long as you have the proper signal on the curve, you can take any measurement and any reading in any order. So now we are going to measure the peak voltage of the resistance. To measure the peak voltage of the resistance, we should set the type to voltage, and the source is math. Our cursor B is already at 0 volts, so we don't need to adjust that. We have to move the cursor A to the peak of the math curve, which is this purple or bluish curve. So once I take it to the peak, I see that the voltage of the resistance is 2.88 volt, which should be recorded in the table. So we have recorded the required parameters for the RL circuit, and the RL circuit is now complete. Now we are going to implement this RLC circuit. So we are not going to need any extra components. We are going to use all the components that we have used in the RC and RL circuits. So we see that in this configuration, the resistance is connected in series with both the inductor and the capacitor. So in the breadboard we already have the resistance and the inductor connected, so we are going to have to attach the capacitor that we used earlier. So for this circuit, what I am going to do is I am going to remove the oscilloscope first so that I can get some room. We see that the resistance and the inductor was connected in series. We are going to move the inductor. So we have moved the inductor to a new node, and we are now going to connect the capacitor in series to this inductor. We are going to place the plus side with the inductor node and the other to the ground. The resistor, inductor and the capacitor are connected in series. Now we will connect the source. As previous, we are going to connect the red wire to the resistor and this black wire to the ground, which is with the capacitor's other end, which is here. The source has been connected appropriately. Now we will connect the oscilloscope. This is channel 1 of the oscilloscope. As always, I will connect the black wire to the ground and the positive wire to node A. We have connected channel 1 to node A. We are going to connect channel 2 to node C. So this is channel 2. We are going to connect this black wire to the ground and this positive end of the probe to node C, which is the capacitor and inductor junction. So we have connected channel 2 in this node, which is node C. Again, we will follow the same procedures. We have to set 10 kHz and 3 volt max to the source. So we have to set that from the function generator. As you can see that in the function generator, the output frequency is 10 kHz and the sinusoid has been selected in previous circuit setup, and it's still there since we did not reset the function generator. So we have to adjust the amplitude and reading from our oscilloscope now. So our cursor is turned on. We should turn it off, and the math signal should be turned off. So this is the current setup. Okay, so now we see that both of the channels are in the equal 1 volt per division setting. So we know that channel 1 was connected to node A, which will give us the source voltage, and channel 2 is connected to node C, which would give us the voltage of the capacitor. So by pressing measure, we see that channel 1 Vmax is 2.76 volt, but it should be 3 volt. So we have to adjust the amplitude so that our peak voltage is adjusted to the required level. Okay, so we are getting 3.08 volt, which is good enough. So now we will start taking the readings from our circuit as our source has been set. So 10 kilohertz and 3 volt peak is our source. So we're ready to take readings. Directly from this setup, node C gives the voltage of the capacitor. So we'll record the channel to Vmax, this voltage 680 millivolt as the voltage of the capacitor. Okay, so the voltage of the capacitor is 680 millivolts. We will now record the phase. We see that the channel 2 is 600 millivolt, which is the voltage of the capacitor. Now we will take the time delay reading, which is the phase calculation. Before doing that, we see that from with reference to the axis, the source voltage comes before the peak of the capacitor voltage, so the capacitor voltage is lagging. So our symbol should be minus. Now taking the readings, we should turn the cursor mode to manual, and we change the source to channel 1 or channel 2. The type should be time. So I take cursor A to peak of channel 1 and cursor B to the peak of channel 2. As previously mentioned, you can zoom in to take more accurate readings. So you can see that the value here is 24 microsecond, which we will record in our data table. We have recorded the time delay of the capacitor is 24 microsecond, and since it is lagging, the symbol is minus, and we've calculated the angle to be 86.4 degree. Now we have to take reading for inductor and resistor. So after capacitor, we'll take the reading for the resistor. From the circuit diagram, we see that the voltage of the resistor is voltage of node A minus voltage of node B. So VA minus VB. Our channel 2 is currently connected to node C. We have to connect it to node B in order to get the voltage of node B, so that we can take the required readings of the resistor voltage waveform. Moving to our circuit, we'll move this channel 2, which is connected to node C, and place it to node B, which is in this node. So I will disconnect it from node C and place it to node B. So as you can see, the probe has been moved from node C to node B. The oscilloscope is now showing node A, which is the source voltage in channel 1, and node B voltage in channel 2. As discussed earlier, we need to calculate the voltage of the resistance, which is VA minus VB, which is channel 1 minus channel 2. We can do that by pressing the math button, and as you see that the operation is already selected as subtraction. Source A is channel 1, source B is channel 2. So this new waveform is our voltage of our resistance, and we have to take required calculations by reference to this waveform. To take the readings, we need cursor. So let's move on to cursor. The cursor is already turned on, the mode is manual. The type should be voltage to take the voltage reading. The source should be math, since we are taking the math reading for the math waveform. So cursor B is already set at 0 volt. We have to move cursor A to the peak of the math waveform, the purple waveform. So by moving the cursor, we now see that the voltage is 2.72 volt. So this voltage should be recorded in our table. Now we will take the time delay reading. To do that, we have to change the type of measurement of the cursor to time, and source is selected to math, which is alright. So if we zoom in and turn this menu off, we can make a better approximation. So let's move cursor A to the peak of the source voltage and cursor B to the peak of the resistance, and we see that the time delay is 0, so the phase would be 0t. So we record 0 microseconds and the phase is 0 degree. Going back to the circuit, we now need to measure the voltage of the inductor here. To measure the voltage of the inductor here, we need the voltage of node B and voltage of node C. Then by calculation, the voltage of the inductor would be voltage of B minus voltage of C. Now we can get only one node voltage from one channel of an oscilloscope, so we would need to connect channel 1 to node B and channel 2 to node C, or we could just keep our current setup where channel 2 is in node B and move channel 1 to node C. Either ways, we will need to move two channels to these two nodes. Now for phase calculation, we would always need the source voltage and compare the phase with the source voltage waveform. If we move the channel from node A, we will no longer have a source voltage waveform in our screen. So before removing the channel from node A, we will utilize the reference function of the oscilloscope, which we can use to store the source waveform, and then after setting up the channels for measuring inductor voltage and phase, we can use that reference signal for phase calculation. Before removing a channel 1 from node A, we want to store the source waveform, which is channel 1 waveform, in our oscilloscope, so that we can refer back to it later for phase calculations. Let's turn off the cursor for now and turn off the math signal. Let's readjust this time setting. So the important thing is, when we store the waveform, we can no longer edit it when we recall the waveform. So whatever settings you have for channel 1 and the time settings here will be the version of the waveform that is stored in reference. So it's important that when you are making the measurements, you keep this time base same, otherwise you will not get an accurate phase calculation. Since I'll be needing only need to save only one voltage in this experiment, I will save at 25 microseconds. So to save it, I'll press reference. Source would be channel 1 because I want to save waveform in channel 1. Reference A, there are two slots, reference A and B. We're going to use the reference A slot and press save. Since reference A is on, the waveform is being displayed in our screen. If we turn it to off, the reference signal will no longer be shown. Okay. So now we can remove channel 1 and connect it to node C so that we can take the readings of the inductor. We will now move the channel 1 from node A to node C. So you can see that here. So I'll disconnect channel 1 from this node A and connect it to node C over here. So channel 1 has been moved to node C, and channel 2 is already in node B from the previous setup. Okay, so since we have channel 2 in node B and channel 1 in node C, our inductor voltage would be VB minus VC. So it would be channel 2 minus channel 1, since channel 2 is connected to node B and channel 1 is connected to node C. Here we see the condition when we connected channel 2 to node B and channel 1 to node C. By using math, the operation is minus. Source A should be channel 2, since channel 2 is in node B, and source B should be channel 1, since channel 1 is in node C. So B minus C, VB minus VC. So this waveform, this purple waveform, this is our inductor voltage. So we can measure the voltage by using cursor as previously shown. We turn the mode to manual. The type is voltage, source is math. Already cursor B is in 0 volt. We move cursor A to the peak of the math signal, 600 millivolt. We should record this in our table. So 600 millivolt has been recorded as the inductor voltage. Now for taking the phase measurements, we need the source voltage, and the source voltage has been saved in the reference function, and we didn't change the time base. We saved the reference in 25 microsecond, and our oscilloscope is in currently 25 microsecond, so we can easily make the reading. To turn the reference signal on, we need to press ref, and we saved in reference A, and the reference A has been turned on. So we see that this gray signal is our source signal. Now to determine the phase, you see that with reference to the axis, the source comes first and then the peak of the inductor voltage. So we can say that the voltage is lagging in the inductor. So the symbol should be minus. And to take the reading, we again utilize cursor. We change the type to time, move cursor A to peak of the source, which is the reference signal, and cursor B to the peak of the math signal, which is the inductor voltage. So the del T, 45 microsecond, is the time delay. We have found that the time delay is 45 microsecond, and the symbol is plus, because the symbol is minus because the inductor voltage is lagging. We must be very careful while taking the reference signal for taking measurements. We have to see that if we have properly saved the signal, because we cannot manipulate it later. So in this case, we see that the reference value which we had previously taken was not saved properly, so we saved it again. Now we are getting the predicted result. It's always important to take reference of your theoretical calculations, which will make your practical calculations make sense. So with reference to the axis, we see that the peak of this inductor voltage comes first, and then the peak of the source comes. So therefore the inductor voltage is leading. The cursors have been placed in the peaks of these two voltage waveforms, and delta T is 23 microsecond. So we can say that the phase of the inductor is 23 microsecond leading. So we will record that in our data table. So we calculate that 23 microsecond is the time delay and the voltage is leading, so the symbol is plus. So 23 microsecond into 10 kilohertz into 360, so 82.8 degrees are angle. So by taking this reading, we have completed all the required readings that we need for this series RLC circuit. These percentage differences can be calculated to see how well our experiment worked out. So this is experiment 3 completed.